Dear friends, a very good morning to all of you. Wish you all a very happy new year. As you know, Maths Aspirants groups organizes online problem solving sessions to help the students who prepare for competitive examinations like NET, GATE, NBHM, JAM, etc. As a part of that series, today we have Mr. Bappa Ghosh is with us. He will discuss some topics related with the theory of complex functions. Mr. Bappa Ghosh is now doing Ph.D. at Indian Statistical Institute, Kolkata. He has done post-graduation M.Math from ISI Kolkata itself, and he qualified National Eligibility Test in June 2019 with All India Rank 4 and GATE examination in 2020 with All India Rank 12. Also, Mr. Bappa Ghosh secured NBHM Fellowships for Masters as well as for Ph.D. He actually belongs to, he's a native of Nadia, West Bengal. And I am very happy to introduce Mr. Bappa Ghosh to you all. And I am sure that today's session will be really useful and helpful, especially in solving the problems related with complex analysis. I express my sincere thanks and gratitude to Bappa Ghosh for joining with us on this Sunday. I welcome all of you to this event. Thank you. Well, over to Bappa Ghosh.
Thank you very much, sir. Okay, so I'll try to motivate things as I learned it, and hopefully it will be helpful to all of you in future. So let us start. So I'll begin with some definitions of differentiability and continuity on several variables, because you can see that C is itself R2. R2 means it's, R cross R, so the functions from R2 to R2 is going to be functions in several variables. So, okay, so let us look at the continuity. Okay, so let F from R2 to R2. You can also assume that it is from Rn to Rm. It's a function. Then, and also assume that X is in your R2, in the domain. It is in the domain. Then we say that F is continuous at X if given any epsilon positive, there exists a delta positive such that for all X is for all H inside B0 comma delta f of X plus H minus f of X, this is less than epsilon. So what does it really mean? It means that suppose this is your ball, this is your Rn, and this is your Rm, and this is your function f. It takes your X to f of X, and this is your epsilon ball. This is your delta ball. And what does it mean? It means that if you take any X plus H inside this, so this is your X plus H, so that will go to somewhere in this ball. So that is your f of X plus H. Okay. Now, Now let us look at differentiability in one variable. I'm not giving example, you know, a couple of examples. Let me give one or two. So examples. So let f from R2 to R2, let's say, are defined by f of xy. Let us give me phi is equal to x square comma y square f2 x comma y is equal to xy x square y, something like that. These are all continuous. One not continuous function, how will it look like? That I give from R2 to R, and let us define f of xy equal to xy y x square plus y square when xy is not equal to 0 and 0 if it is the origin. Okay, so yeah, so why it is not continuous? It is not continuous. You can see that. You'll see that a is not continuous at origin. So let us look at why. So the proof is the following. So what I have said, that for continuity we'll get a delta, given an epsilon, we'll get a delta ball such that its image completely lies inside this ball. I mean this ball. The image of this ball has to go to inside this ball. Okay, so I mean, what does it? What is the negative statement of that? It says that I mean you will find an epsilon for which if you take any delta ball, however small, you will find a point here that goes outside your epsilon ball. So in other words, you'll get a sequence or a direction for which, I mean, a sequence is enough. You will get a sequence for which your image, I mean, image will not go inside those epsilon, will go into that epsilon ball. So yeah, so I'll try to do that. So okay, take this y equal to mx line, this line. So that is this is 0, this is y equal to mx. M will vary, okay. For the timing, let us look at just y equal to mx. So if you put m not equal to 0 as well, so if you put it there, what you get? F of xy you get as m x square by x square plus y square. So x square plus mx square. So what you are getting? M square x square. So 1 plus m square. Oh yeah. So you are getting this. Now if you take m not equal to 0, if you take m equal to 1, you get some value. What are the values? If you take m equal to 1, you get this guy to be 1 by 2. If you take m equal to 2, you get this guy to be 2 upon 5. So you see that when you are approaching from two different directions, these two different directions, you are getting two different values at the point 0. So the function is not continuous at the point 0. Okay. So why is this function important? This will come again. I mean shortly when I talk about differentiability and all. Okay. So now let us look at differentiability on R. You know the definition. So what is that? We say we say that f is differentiable at x if the following limit exists. If the limit exists. So what is that? F of x plus h minus f of x by h. This limit as h tends to 0 exists, and you denote it by f prime x. Denoted f prime x. But problem in several variables or in R2 is that we cannot divide a vector by another vector. So we have to somehow modify this definition, but it is still a very good definition for complex analysis or in C, because we can divide by a non-zero complex number. So okay, so how do we get to that point? See, by continuity I have written something here. So have a look at this. By continuity I have written something here, and now by limit you also know that the epsilon delta definition, given an epsilon there exists a delta such that f of x plus h minus f of x by h. I have denoted that derivative by this. That means this guy will have to be less than epsilon for all h inside this. So that's the definition of your, the limit. Yeah. So now if we just multiply by h on the both sides, what you get? This thing less than epsilon times mod h for all h inside V0 delta. So now if you say that this thing is the error term, so f of x plus h minus f of x minus h times f prime x, this error term has to satisfy the following property. Yeah, for all h inside in a suitable neighborhood. Okay. So this is how we look at the derivative, but now the derivative itself has some other meaning as well. So this is our derivative. We define a function from R to R itself, which is a linear map that takes h to this thing. So you can also check, that's a homework, that the linear functions, linear maps T from R to R is given by multiplication by multiplication, and the factor is lambda equal to T of 1. One can check that. Okay. Now let us look at the definition of differentiability in several ways. So let f is a function from Rn to Rm, and this is also true, by the way, for open sets in Rn. This is open. I'm not writing it. I'm just keeping myself restricted to Rn. But yeah, it should be well understood that if you take any open subset, that is also going to work. So yeah, without doing this, let me do this. U subset of Rn, this is open. F from U to Rn is open, and X is in U. We say that F is differentiable at x if again there for all epsilon positive there exists a delta positive such that f of x plus h equal to f of x plus tx of h. I'll say what are these things plus e of h for all h inside b0 of delta such that e of h is less than epsilon times norm h, and tx of and this has nothing to do with that thing. Tx is a map from Rn to Rm, which is linear. Is a linear map. Comma 5. It's a linear map. Okay, so yeah, so linear. So now let us look at. So I hope it is well understood to everybody. Now look at what is called the partial differentiation. So before that, let me talk about directional derivatives. What is a directional derivative? Directional derivative, let's take an f is a function from Rn or open subset of Rn. U to Rm and B is a vector in Rn. Then we say f as a directional derivative. We say that directional derivative of f exists in the direction. We say that the directional derivative of f exists in the direction b at the point x if the following limit exists, and that is limit t tends to 0, t is a real number, f of x plus tb minus f of x by t exists, and denoted db of f at the point x. Now we say the partial derivative. Now, what are the partial derivatives? Partial derivatives are the directional derivatives in the direction, in the coordinate directions. Let's say this is our Rn, this is our Rn, and I'm talking about differentiability at the point 0. So these are my derivatives along these directions, even on the other side. So the derivative along these directions are called the directional derivative. So del f del xi is the derivative in the direction ei of f at x. Okay, so now fine. Now what is the relation between the derivatives and directional derivatives or partial derivatives? This is captured in the following theorem. The theorem says let f from u to Rn Rm and x in U, the function f from the function suppose f is differentiable at x, then the directional derivatives of f at the point x is nothing but Tx of v. So remember, Tx was a linear map from Rn to Rn, and we also often denote Tx as this dfx. Okay, so this is dfx at in the direction of v. This might be familiar notation to all of us. Then dfx has the matrix notation del f. So f, suppose f1 up to fm, then this is del f del x1, del f1 del x2, and so no del f1 del xn and up to del fm del x1 del fm, and you know what I mean, del fm del xn. So this is my directional derivatives. I mean, this is the total derivative, and this is how it is given in the this is what the matrix look. I mean, every linear map from Rn to Rn, it's a matrix. So this is the matrix representation of this map. Okay, fine. So okay, now another. So this theorem raises a question whether if we have the derivative, all the partial derivatives or the directional derivatives exists, can we say that f is differentiable at the point x? The answer to that question is no. And a counter example is, take the function I defined earlier, xy by x square plus y square, when xy is not equal to 0, 0, and 0 if xy equal to 0. You have seen that it is not even differentiable, so there is no question of this is not continuous, so there is no question of differentiability at the point 0. Okay. But let us check that all the partials exist at least. So f of x by f of 0, 0. So dvf in the direction of x. How does it look like? At the point 0, dv. So f of t times v minus f of 0, 0 by t. So let me say that this is limit t tends to 0. Let me say that v equal to v1, v2. Then this is dvf 0 equal to limit t tends to 0. This is t times v1 times t times v2 by t squared. Oh, I guess this is not going to work. This is not going to work. So you probably have to raise it to 2. This is going to be 3. This you can check again. This is not continuous at the point. So okay, let me just check whether it is differentiable at the point, whether the partials exist or not. Probably this will work, and for this all the direction, but other function will also work for the partials in the direction of in the coordinate directions, that the partials will exist. So del f del x equal to limit t tends to 0 f of t times t times 1 comma 0 minus f of 0 0 by t. So that is, you can check, that is 0. Also del f del y will be 0. So yeah, but the function is not the continuous at the point 0. Okay. So now I'll look at what is called the holomorphic functions.
Sir,
Yes.
sir, I have a doubt.
Yeah.
Sir, for I'm asking for suppose two variable function. Sir, if
Yeah.
the condition is like if the one of the partial derivatives both the partial derivatives exist and one of the partial derivatives is continuous,
It's
then the
continuous.
function
Then
is
yeah.
it true or yeah?
Yeah, it is true. So that's a homework. Let f is a function from R2 to R or any Rn to R. Then if all the partials exists and it is n and n minus one of them is R, n minus one of them are continuous, then f is differentiable at then continuous at x. Okay, then f is differentiable at x. Yeah, thank you for finding out. I was missing this. Okay, so holomorphic function. So before holomorphic function, let me talk about some linear algebraic requirements. So you know C is a vector space over R. Correct. Now you can, if you have a function, a linear map, linear means R linear map from T from C to C, then you can, and you know that this is a basis of C over R. Now if T of 1 equal T of 1 equal to A plus IB and T of I equal to C plus ID, you know that the matrix in this basis is A, B, C, D. Okay. Then okay. So then now I'm talking about something more. C is also a vector space over C. Is a vector space. Now my question is this suppose this is suppose T is C linear. I can say when it is C linear or not. So you can check that it is also R linear. Now when is this guy is going to be and how does this guy look like? So now R linear function, R linear map is going to be C linear if T of x, this is equal to x is in say C, then x times T of 1, which is nothing but x times A plus IB. So T of I is going to be I times A plus IB, which is nothing but IA minus B, that is C will be equal to minus B and A will be equal to your D. So okay, so T is C linear if it is true, if then C equal to minus B and A equal to D. But the converse is but the converse is also true. And okay, converse is also true. So let me look at phi. Suppose t of 1 equal to a plus ib, and your t of I equal to ia plus b, ia minus b. You can check that. That t extends to a C-linear map from C to C. This is an easy exercise. Okay, so we see that you can also see that T is C-linear. Then T from C to C is nothing but multiplication by T of 1. Okay, that is also another exercise. Okay, so now let me define what is called a holomorphic function. First, complex differentiable. So complex differentiation. Let f is a function from an open set of C to C, and z naught is in C. We say that f is complex differentiable at z naught if, just a minute, let me drink some water. If limit h tends to 0, f of z naught plus h minus f of z naught by h exists, and we denote it, and we denote this by f dash of z naught if it exists. Now we say f is holomorphic at on U if the function f is complex differentiable at all points of x, at z for all z in U. Okay, so now we have a equivalent criteria. So now we have a theorem. Equivalent criteria for complex differentiable, complex differentiability. We will check that it is also related to what we have just seen in the terms of linear algebra, and also it is also related to the differentiability definition we have defined, and this also gives birth to something called the Cauchy-Riemann equation. So the following are okay. The following are equivalent. So what are they? The function. I have assumed that f is from U to C. So that, and z naught is in U. The function f is complex differentiable at z naught in U if and only if the function f is differentiable at z naught and the derivative is C linear. Number 3, the function f is differentiable at z naught and So f you assume to be u plus iv, and del u del x equal to del v del y, comma del v del x equal to minus del u del y. So this is what is important, and if one of the above is true, then we can write f prime z naught to be equal to del u del x plus I time del v del x. Proof is not hard, this is easy. So 1 implies, so first let us look at 1 implies 2. So suppose it is complex differentiable at the point z naught. So again you can write it f of f prime z naught is equal to limit h tends to 0 f of z naught plus h minus f of z naught by h. Now you define something called t of h is equal to f of z naught plus h minus f of z naught minus h times f prime of z naught. You have seen that if this limit exists, then this e of h satisfies this property. So f is there any question? Okay. So f is differentiable at z naught, and I mean, what is the derivative here? This thing. So here t of f prime z naught is, you can check that this is C linear. This is given by lambda going to lambda times f prime of z naught. Okay. So now 2 implies 1. 2 implies 1. What do we have to assume? Okay. So suppose the derivative exists. So the derivative is this. Then you know that f of z naught plus h equal to f of z naught plus h times f df z naught of h plus e of h. Now f of z naught plus h by minus f of z naught by h minus, okay. So you know that this thing is C linear. So this is basically h times df z naught of 1. So this is df z naught of 1, and this is equal to e of h by norm h. So you know that this guy goes to 0. So f is C differentiable at z naught, and the derivative f prime z naught is equal to df z naught of 1. Now 2 if and only 3. 2 if and only 3. So you see that the function f is differentiable at the point z naught. This thing is common. So the derivative is C linear, has something to do with this thing. So what is the derivative? So the derivative df z naught is equal to del u del x at the point z naught, del u del y at the point z naught, del v del x at the point z naught, and del v del y at the point z naught. So you have to see that when it is C linear, if and only if these guys are equal and they are opposite to each other. I mean, their sign is opposite to each other. So that is what the Cauchy-Riemann equation also says. This is. So this is done. Okay. Now, let us go towards analyticity. Okay. So let us go towards analyticity. Okay. So, okay, let gamma from A to B to C is C1. We define the length of gamma, which is denoted of gamma, denoted L of gamma. This is equal to A to B, F prime, F of gamma T, gamma prime T dt, and we define the and let F is holomorphic from C to U to C, such that image of gamma is contained inside U. Then we define the integration of F with respect to gamma by this integration A to B F of gamma T, gamma prime T dt. You can check now the ML estimate. So that says that with all these assumptions, this Z satisfies this. I'll introduce all of them along the way. So gamma F dz, this is equal to, this is less than or equal to A to B F prime F of gamma T, gamma prime T dt. All of them are in the modulus. So this is less than or equal to supremum of F gamma T, so supremum in T A to B, integration A to B gamma prime T dt. So this is your M and this is your L. So that is M is the supremum of F of gamma T. T is in AB. Now why does this supremum exist? Because AB is a compact interval, F compose gamma is continuous, that's why. So this is equal to ML, the ML estimate. And L equal to, of course, the length of gamma. Now I'll assume few things and I'll quickly look at few problems. So there are few things like Gurdjieff's theorem that says that let F from U to C be a holomorphic function, then let delta be a triangle inside U, then integration over delta of F dz, this is 0. I'm assuming these things because I don't have much time to prove all these things. And then next lemma is let F from U to C be a continuous function such that integration over this is this delta. The triangle means this. This is your U, the triangle means everything, and delta means just the boundary of the triangle. Okay, so suppose this is equal to 0 for all delta content inside U, then F is holomorphic. So how does one do this thing?
Hello, sir. Hello.
Yes.
Is it necessary to be triangle? It could be any closed curve. I think circle, or will it be true?
Yeah, it is true.
So why it is only triangle only for particularly? Hello.
Sorry. My laptop got turned off. Okay, so let me continue from here. Can you hear me?
Yes. My question is, why it is only particularly triangle? It's
No.
closed.
If you are assuming for every curve, then it is of course for triangle. So I am assuming less.
Okay. Means it will satisfy for closed curve also in circle. If we take other than triangle, if we take other things.
Triangle, except triangle, other things means.
If I take a dix example, if I take a dix inside U.
Okay.
Will that be that integration over that dx f dz will be 0? I think it
No.
should 0.
See, you have to integrate f along something called a curve, or these are called one chains. So you have to somehow integrate against some chain, some image of continuous image, or at least not C1, piecewise C1 functions from this gamma from 0, 1 to U. So you have to integrate along this one chain, not two chain. The function f dz is a one form. It cannot be integrated against two chain. You understand? It cannot be integrated over any surface. It has to be.
So then why my question is, then why did you drawn that whole that in above slide you have drawn that whole
This U.
inside you have taken whole triangle. It should not be whole triangle. It only should be side will be there, right?
No. I'm saying
Triangle.
that. No. I'm saying that if this hole is there, and the triangle is like this, along this triangle it will not be 0. I'm not considering all those triangles. I'm considering triangles whose interior inside U. Okay, this hole, if this hole is there, I'm not talking about those triangles. If holes
Then
are
my
there,
question is.
yeah.
Then my question is, then if I take a circular shape and I am taking hole inside thing, will that be 0 if you integrate over that?
No, that will not be. There are theories for that. Okay.
Go ahead.
Okay.
Sir?
So yes.
Sir, why are you giving preference to just triangles? When we studied the Gaussian theorem, it was for any closed curve which is inside U. So is there any special thing about triangles?
Yeah. So when you are saying that any closed curve with interior inside U, so triangles are less than that those things. When we prove the Gaussian theorem, what we do, we take a triangle, we take the midpoints of the triangles and we divide them, and then we keep on dividing them. Okay, so thus we get a nest of compact sets with and the single point will be there. So if you integrate against that single point, so that will give you 0, something like that. And if you take if you consider any curve like this and its interior is there, and you are assuming that for that gamma it has to be 0, then again when you are assuming all these things, you are at least allowing you these triangles. So the assumptions are less than every curves, and the triangles are important. I'll show you in this proof why it is important. Okay, so just bear me for a few minutes. You will see. Okay, so this is my U with this hole. Possibly this interior this thing is not there. Possibly this yellow shaded region is not there, or the red shaded region is not there inside. So let's say, sorry. Let's say this is my Z0. I want to show that if my claim is okay. What did I say? F is differentiable. No. I'm assuming more thing. It will also be differentiable by mod error, but I'm not saying that. So then there exists F from U to C, such that F prime Z equal to F of Z, or all Z inside U. So yeah, what is this? So let's say Z0. This is point, and I'm considering a ball, small ball around this guy, this Z0, such that this whole B delta of Z0 is contained inside this closure contained inside U. Okay, so now we go. My claim is okay. No, I don't have any claim at the point. At this point, okay. So let me take this Z plus H, and once more, I cannot allow these holes. Sorry. Okay. So let U be convex. U be a ball. Okay. And this Z not be the center. Let me be simple. Okay. Now these points, this is my Z plus H. This is another Z, and this is my Z plus H. So this forms a triangle. That is why the triangle is important. Okay. Now you know that integration over this triangle of f of z dz, this is equal to 0. Now define f from U to C by f of z equal to integration over z naught to z f of z f of zeta d zeta. Now I'll show that this f is differentiable and f prime z equal to z for all z inside this this bond. Okay. Okay. Sorry. So I'm just writing out the definition. So what will be f of z naught? So it will be the card going from z naught to z plus h f of zeta d zeta. So subtract these two minus f of z by h. This is equal to 1 upon h integration. So this, you see that over this triangle this is 0, over this triangle this is 0, and the triangles are oriented anti-clockwise. Okay, so this is going to be z to z plus h. Why is that so? F of zeta d zeta. You see that first I am going from, okay, let me draw it here. So this is z naught plus h, sorry, z and z plus h. So this is my triangle. This is the first integration. This thing z naught, and this is this in this direction. So to complete the triangle, you have to go this side. So that's why this z to z plus h. Okay. Okay. So, okay, now f of z plus h minus f of z by h minus small f of z. This is equal to 1 upon h z2 z plus h f of zeta d zeta minus f of z, this thing equal to, now you see that integration over z2 z plus h f of zeta, and not, I mean just over dz, this is h. So this is going to be 1 upon h integration z2 z plus h f of zeta d zeta minus f of z d zeta, the whole thing. So is there any problem with this thing till now? Okay. So this is less than or equal to 1 upon norm h. This is integration over z2 z plus h f of zeta minus f of z, okay, d zeta. And you see that when h is close enough, zeta is also small enough, zeta is also close enough to z, and since f is continuous, this guy has to go to 0. So this is sorry, so this is okay. So let me take it in this way. So suppose no, not suppose f is continuous at the point z. So suppose and epsilon is positive. So suppose that h is small enough such that f of zeta minus f of z, this is less than epsilon for all h less than delta. So I'm taking my delta h to be small enough, to be close enough to z. So then this will be, now just apply the ML estimate. What will you get? This is supremum over all these things. So that is epsilon, and this is 1 upon mod h integration z2 z plus h, this guy mod d zeta, and this is actually epsilon times 1 upon mod h times this is mod h. So this is epsilon. So yeah, so f is differentiable at z naught and f prime f prime z, it is z, and f prime z equal to f of z for all z inside. So this will be true for even all convex sets, and that lead us to Cauchy's theorem. Cauchy's theorem that says that let U be a open subset, not open convex set, and f from U to C be a holomorphic function. U to be a holomorphic function, then integration over gamma f of z dz, this is going to be 0 for all closed C1 curve. Okay. Now proof says that, see, f is holomorphic for all closed curve.
Yeah, for all closed curve inside U.
inside U. Yeah.
Thank you.
Yeah, thank you very much. So proof F is holomorphic. So that Gurdjieff's theorem implies that integration over delta, the boundary of a triangle f dz, this is going to be 0 for all delta contained inside U. Now that by last lemma, there exists a capital F from U to C such that f prime z equal to z f of z for all z inside U. So that is, we have a primitive. So then f integration over f along gamma f of z dz, this is going to be what? So this is going to be a to b f prime gamma t gamma prime t dt, which is nothing but f of gamma of b minus f of gamma of a. This is actually nothing but integration of df compose gamma a to b. So that is so. Now another important theorem without proof, Cauchy's theorem for homotopic curves. Homotopic curves. So let U be open connected and gamma 1 is homotopic to gamma 2 in U. Then and let's say f from U to C is holomorphic, then integration over gamma 1 of f, this is equal to integration of gamma 2 of f, fz dz, of course, fz dz. Okay. So this is the theorem without proof, and this theorem is a homework. The following. Is there a question? Hello. Okay. So this theorem, someone's mic is turned on.
Last video.
Okay, so next theorem, this is a homework which is Cauchy's integral formula. I'll give all the details, just carry out yourself. The calculation will be done by yourself. Cauchy's integral formula.
Sir?
Yes.
Sir, homotopic means one can be transformed into another, right?
Continuously. I mean, that is, yeah, let me just write down the theorem. The definition, sorry, not the theorem. So let gamma 1, gamma 2 from 0, 1 to U are continuous function. Homotopy between these two curves is a function h from 0, 1 cross 0, 1 to U, such that gamma of t comma 0, sorry, h of t comma 0 equal to gamma 1, h of t comma, this is a continuous, of course, t comma 1, this is equal to gamma 2. So that is, so yeah, so this is a map, h is a map from these to an open set U. What is this saying? So this is our 0, 1, this is our Okay. So this line is 0, this line is again, what is this? 0 cross 1, 0 cross 0 comma 1, and this is 1 cross 0 comma 1, 0 comma 1. So what it does, H maps this line to, this is gamma 1, and H maps this line to gamma 2, and in between this line, how do you go to that curve? There are these beautiful homotopies that leads to upper curve. Okay, this is gamma 2. Okay, so now let us look at the theorem. So we are assuming everything that U is open connected and F is a holographic function. Then what do you say that, yeah, and also assume that let Z0 is in U and B0 and BZ0 comma delta, this is a subset of, once again, okay, this is the subset of U, then for all Z inside this closed wall, not this closed wall, this open wall, you can write f of z equal to integration over this boundary of this wall, or z minus z naught equal to r f of zeta by zeta zeta minus z d zeta. So this is true for all z inside this smaller wall. So this is your u. Here this thing is not in your domain, and this is your ball around z dot, which is, and this is your z. These are your z's. All those z can be written as this. So this theorem actually leads to a lot of things. One of the things is local path series expansion.
Sir.
Yes.
Sir, please explain again the previous one.
This one.
Yes, sir.
So, okay, so let me prove so that you can get.
Sir, did you forgot to write 2 pi I?
Yeah, I forgot to write 2 pi I. Thank you.
And sir,
Wonderful.
can't we say that it is true for any curve lying inside U if U is simply connected?
Yeah, yeah. Then we can say yes. You're correct. Okay, so just a minute. Any simply closed curve actually. That means that curve has to wind around just once. That gamma has to be simply closed. Okay, so let us look at the proof. So let me just write the ball on z0, and this is my z. So suppose this whole thing is r, and I take a small ball around it whose radius is r. So zeta minus z, this is less than r, and what I said, this is of course such that b z comma this small r is completely contained inside this open ball of radius r. Then you can see that this thing, the outer curve and the curve, this inside small curve, these two are homotopic, but just by linear homotopic, this linear homotopic. Okay, so then what do you get? That z minus z naught equal, sorry, zeta minus z naught equal to r 1 upon 2 pi I f of zeta by zeta minus z d zeta. This integration is same as integration over 2 pi I, and this small r, right, zeta minus z f of z by zeta minus z d zeta. This is over the small one. Okay, now this you claim to be equal to f of z. So just let me do the calculation. So, and also you can check one more thing. That f of only this integration over zeta minus z equal to r 1 upon 2 pi I. This is just what dz is going to be 1. So now then 1 upon 2 pi I integration f of not this zeta minus z. This thing will be 1. So as f of z by, just because this is 1, I can write here. I'm just multiplied this thing. This is okay. This is zeta. This thing is equal to this thing is equal to 1 upon 2 pi I integration. This is less than or equal. Okay. So this is over zeta minus z equal to r integration zeta minus z equal to r f of zeta by zeta minus z minus f of z by zeta minus z, everything outside d zeta. Why I can write this? Because this is this d zeta and all these things, this is actually 1. Integration of all these things is 1. I proved it. I claimed it. Just you can prove this is easy. Just prove it. Okay. So this is less than or equal to 1 upon 2 pi integration f of zeta minus f of z by zeta minus z d zeta. This is zeta minus z equal to r. Put zeta equal to z plus r e power it. Then what you get? Basically 2 pi 0 to 2 pi. This is f of z plus r e power I theta minus f of z by what is this? R e power it times I is out, r e power it is again out, dt. So this is this thing. So this is again 1, this is 1, r out. So this is 1 upon 2 pi 0 to 2 pi. This thing f of z plus r e power it minus f of z. These guys are close enough. If r is small, this is close enough. dt. So this is less than epsilon. So this is epsilon times 1 upon 2 pi, and 0 to 2 pi, this integration is 2 pi. So this is epsilon. Okay. So this thing actually eventually gives you local power series expansion. I can't do them all now. Power series expansion, and number 2, which again will give you the Liouville's theorem. Liouville's theorem, it is here, theorem, which says that every bounded entire function is constant, and also the uniqueness theorem. So why is this important? Why is this Cauchy integral formula important? So this is where this is the first instance where the real differential world and the complex differential world differs. This local power series expansion. That means you will find the suitable neighborhood inside every point where you can write this function as power series. That is, if it is a z naught, you can write your f of z equal to this kind of summation. Okay, that is the power series expansion, and your ans will also have some nice expression, which is integration over. Is there any question? Okay, zeta minus z naught equal to small r f of zeta by zeta minus z naught whole to the power n plus 1 d zeta. So that is why this is important, and so every holomorphic function becomes an analytic function, which is not true in just when you just assume that it is a real differentiable function. So that's why everything starts becoming, having its own importance alone, not just as a real differentiable function, but also in the sense of complex differentiable function. Okay, so also okay, so now let us discuss some problem. I don't have much. I'll not have time if I just go over all these things. Okay, so these are the questions that actually help me to prepare for net gate and everything. And also, I'll be honest, I'm not I actually solved as many questions as from complex analysis and linear algebra I could in my net gate and every other exams I faced in my life, and these problems really helped me a lot. So yeah, let me discuss some of them. So choose the correct option. Number 1, there exists a biholomorphism from C to the upper half plane. This is the upper half plane. Number 2, there exists a diffeomorphism from C to H. Number 3, C and H are not biholomorphic but diffeomorphic. Number 3, none of them. So okay, so let me check if it is. Suppose, so option A. Okay, so solution. Number 1. So if it is biholomorphic, then it is of course diffeomorphic. So if let me check if there is any biholomorphism. So what does it mean by a biholomorphism? Two domains in C, U and B are biholomorphic if F is F is holomorphic and F inverse is also holomorphic, which is F is holomorphic and F is bijective. This thing I cannot show you, but this is true. Okay, I mean I could not. Now, okay, let F from H, C to H be a biholomorphism. Then what do you get? Then you apply T on H. What is T? T is this map that takes the upper half plane to D. So what I have done here, this is your C, this is your H. I have just come down to D. So sorry, let me just draw everything. So this is your H, and now just apply this transformation Z minus I by Z plus I. You go inside this D, open this. Then what do you see? That T compose F is a function from C to D, and this is also invertible. This T is invertible. Then what do you get? You get this is a holomorphic function from C to D, which is bounded. That implies that T compose F is constant by Liouville. So but T is not constant. You see that T is mapping this upper half plane into D onto D. So this is not a constant map. So your F has to be constant. That implies F is constant. So if F is constant, then F cannot be biholomorphic. Okay, so that's a contradiction. Okay, so this is not true. Now for option B. So is this okay with everyone? Yeah.
Sir, I have a doubt.
Yeah.
In real analysis, when we used to say that if F is differentiable and F inverse exists,
Yes.
then to say that F inverse is also differentiable, we needed a few conditions that should be defined on an interval, and the derivative should be non-zero at every point.
Yes.
So
Why it is not required here? You get F is open map. When F is non-constant holomorphic, F is open map. Okay, so by default your F of U will be open.
Sir, can you repeat once?
So what I'm saying that if you have a function from U to C, so non-constant holomorphic function, then F of U is open inside C. So what I am saying here, so you have a open interval, open set, and you are going to another open set, possibly leaving out some spaces. So this is again open. So if you take F of Z here, you can also send it to Z. If it is bijective, no? If it is, so with domain of definition there is no problem, and probably you are objecting something. Did I write the definition of biholomorphism? Yes. Probably, yeah. I've said here that this is holomorphic, and F inverse is also holomorphic, and I'm saying that this is enough. This is enough. Okay. So F inverse exists.
Not needed.
No, not needed. F inverse exists is enough.
Okay.
Yeah. For that you need to read the theory of it, but for now you can assume that. Okay. Okay. Yeah. Okay. Thanks for the question. Now I have to check the option B that says that there exists a diffeomorphism from C to H. From C to H. So C to H. So C is x plus iy. I send this to x plus e power iy. send this to I times e power y. You check that for all y inside R, e power y, this is greater than 0. This is greater than 0. So this is inside H. And also, so this is a holomorphic, not holomorphic map, but this is a smooth map. So F is differentiable. Now for the converse, H to C, what do? X plus IY. This you send to X plus I log y. See, again here log is defined because y is strictly positive here. Okay, I hope this is clear to you. And now check that F compose G is is equal to identity on H, and G compose F, G and G composition F, this is equal to identity on C. So what you get that G, so F is C to H is a what is called, it's a diffeomorphism. Okay. So again, also you have to notice that this is also C1. This is also this is also smooth, more than C1. Okay.
Sir, sir, can you explain that what is diffeomorphism do? Like what is where it takes that number x plus iy?
X plus IY. So yeah. So suppose this is your C, and this is your upper half plane. So what it does, it takes a point here to a point here, somewhere here. So your question is not clear to me. Can you ask it again, please?
Diffeomorphism, like what is its meaning?
So diffeomorphism means the differentiable properties are same. So by that, what do we mean? As the differentiable categories, they are same. That means if you take a function from, if you see a holomorphic function going out from this, not holomorphic function, but smooth function going out of this, the set of all smooth function, that is C infinity of this C and the C infinity of H. These holomorphic, the set of these things are isomorphic. They are isomorphic as modules, C module or R module. So yeah, so one of the things that we mean same to be same when we say that the two spaces are diffeomorphic. These two guys are same. Any differentiable property. Let's say this is diffeomorphic to some other domain, then it will also be. Okay, so is it what you want to ask?
Yes, thank you.
Okay. So then the next question is, okay, now next question is C star is, and this means biholo, okay, biholomorphic to D star, whether this is true. So before going to this, let me give you a homework, that is Riemann's theorem for removable singularity. It's a pity that I could not talk about singularities, but those are really important things of complex analysis. Not only for exams, but yeah, those are really central thing in those are really central things in complex analysis. Okay, so removable singularity. So what is that? Let's say A is a function from punctured neighborhood of Z0 to C is bounded. It's a holomorphic function, holo and bounded, and then F has a removable singularity, but I can define it for you. What is that? I can give it another name, that is f of limit z tends to z0, f of z0, f of z exists, and if you call that f of f of z0, then f is differentiable at the point z0. Let me prove it. So how does it prove? How does one prove it? So also, I'm just okay. So also it has another way to say, f is f has removable singularity at z0 if and only if and only if f has the coefficients of negative powers of z minus z0 power n is less than 0 are 0 in the Lorentz series expansion of f around z0. Also, again, I have not talked about this guys, and also these things are something what I have not defined, but those who know so the Lorentz series, in the Lorentz series expansion, these ans are given by this 1 upon 2 pi I f of zeta minus z0. This is equal to small r, and small r is something so that r is less than epsilon by zeta minus z0 all to the power n plus 1 d zeta, and now assume that n is less than or equal to 1, then mod n, this is less than or equal to, what do we have, 2 pi integration over zeta minus z0 equal to r f of zeta by zeta minus z0 to the power n plus 1 d zeta. Now you just put zeta equal to z0 plus r e power it, then you get 2 pi integration 0 to 2 pi, and this is bounded on this punctured domain, hence it is bounded here. So this is less than or equal to that bound n by, this is what? This is r to the power n plus 1, and this is d zeta. You see that it is ri e power it dt, and if you take d zeta mod, this is r dt, this is r dt. So what is this? This is 2 pi 0 to 2 pi n by r power n dt. So this is r power n, but n is less than or equal to minus 1, sorry, n are minus 1. So minus 1 means it is, r to the power minus n. So okay, we'll write it r to the power minus n, and this goes to 0 as r goes to 0. So So I hope it is clear. So what you get that I mean, in terms of this, you can, you can say that F has a removable singularity at the point Z0. Okay, but yeah, one needs to prove that equivalent criteria before saying this. Okay, so yeah, it will be needed in my. So my question was that C star, is it diffeomorphic to D star? So you see, there is one C star to D star, that is here to, this means this point is not there, to this without this point. This is my D star. So since it is holomorphic, F is holomorphic and its image is bounded, that means this point has removable singularity. So it has to go somewhere. Yeah, I mean, so F of C is a subset of D closure. So this point has to go inside D star closure. So which is nothing but D closure, which is a subset of which is actually D closure. So you see that it is still bounded. The image of F still bounded, is bounded. So again, it is the entire function bounded. So apply Liouville. That says that F is constant. And if it is a constant, it cannot be onto. Okay, so it's not, so F is not biological. Okay, so but is it diffeomorphic? And the answer is yes. How do you give the diffeomorphism? You see that C star is you can map it to here C2, okay, from C to H, and then you go by Z minus I by Z plus I to your D. So why does it take? This is a so this map was x plus I into e power y. So this map was this, and what was I mean, it taking to the 0 was going to first 0 plus I times e power 0, which is I, and I was going to, you see that I minus I by I plus I, which is 0. So 0 was taken to the origin. This is 0 plus I. So origin is going to origin. So if you restrict this map, this is let's say my G. So G restricted to C star is diffeomorphism with D star. Okay. So again, another question related to this thing that says that D star is not diffeomorphic to this annulus. Any annulus, I mean, not only this, any annulus you take with any annulus, I mean, epsilon less than or equal to mod z less than or equal to r prime, but epsilon has to be greater than 0. This is, I mean, for any annulus of this form, D star is not diffeomorphic. Epsilon r prime. So just let me prove this, and you can easily show that this will also not work. Just analog proof. So D star to 1 less than equal to mod z less than equal to r, let's say. So suppose there is a function here. So if such a function is there, so I'm mapping D star to annulus like this. And also this also we should be noted that instead of 0, this can be also Z0, and this is my region around Z0. Okay, so let me take it Z minus Z0. Okay, so yeah, you see that suppose this such a kind of map exists. So if such a map exists, then you see that f of d star is bounded, and f of z is mod of f of z is less than equal to r for all z inside d star. So again you apply Riemann's theorem for removable singularity, and you say that f of 0 will 0 has a removable singularity. At 0, f has at 0, f has removable singularity, and just a minute. Okay, so yeah, so that means this 0 has to be mapped to somewhere on this annulus. Okay, so 0 has to go to somewhere in this annulus closure. So it can be either on this boundary, or inside. So suppose this goes to inside. So f, now it is a bar from whole of d closure, d to this. So this 0, if is it, so f of 0 may be inside A, or f of 0 inside the boundary. So in the first case, f of 0 inside A. So that means this omega equal to f of 0, this is inside A. And now f was a, this is a bar, okay. So f was a map from d star to the annulus. So by default, f inverse omega had another image, another pre-image inside D. So call that Z. But do you see that Z is not inside D star? So that implies Z is not equal to 0. So now 0 and Z are going to the same point, and if you take let me draw it in a bigger thing. Now this is my 0, this is my Z. So you take two suitable neighborhoods. And they are going to interval to those image of two neighborhoods are like this. This is, let's say, this is omega z, not bz, and this is b0. So let's say this is bz and this is b0. Do you see that there is a overlap? So these two portions are going to the same thing. So every point here has two pre-images. So every point here has two pre-images, one here, one here. So the injectivity fails. So that doesn't work. So what we conclude from here, that this f bar of 0 has to go to delta A. But again, if it goes to 0, delta 0, D is open. So f bar of D, this is going to be open again in C. But if you include a point inside delta A, so that is not again, so either here or here, that's not open. Because when you take a neighborhood around this point, it's going outside, this point it's going outside. So no neighborhood is contained wholly inside a closure. Okay, so it's not open. So that concludes this thing. Now let us look at
Sir,
yeah.
Sir, that punctured disc and annulus are homotopy.
Puncture disk and homotopic. Yes, they are homotopic. So how do you show that they are homotopic? So you take okay. So let me show you here. So this is your annulus, let's say. Okay. So what you do, you just take this linear homotopy. Just take this linear homotopy. So this is going to be some dr star, and dr star is homotopic. This is homotopy, okay? One will be less. So this is again. This is dpure. This is biol. 2d star. Okay, dr star means ball of radius r. Okay, so yeah, I guess I'm clear enough. Okay, so next question.
So it means that there is no implication in like homotopic and diffeomorphism.
No,
I was thinking about that. Like if they are homotopic, then it will necessarily.
No, if they are diffeomorphic, diffeomorphism implies they are, what is that called? Homeomorphic. So, and homeomorphism is stronger than homotopic. So, is that?
Yeah. Okay, sir. Okay. Thank you.
Okay. So, okay, now the question f is from C to C, so entire function, and f of z equal to u plus iv, let's say. These are our assumptions, and there is one set of assumptions that u square minus v square is equal to constant. Then what can you say about f? Is f is constant, non-constant? Can anyone say? What is your guess? So let me say f is constant. How do I prove? So one.
So the ᴑᴇᴏ theorem.
Sorry.
ᴑᴇᴏ theorem.
Liouville theorem. Yeah, we have to use. But here you see u square v square, not uv. Not u square plus v square. Okay. So I cannot say that. Liouville theorem says that u square plus v square, this is bounded, but not u square minus v square. Okay. So one can probably try to use Cauchy-Riemann and say, but let me give you another way to prove that thing. So f is constant, f is entire. That implies f squared is also entire function. And if f of z equal to u plus iv, that means f square equal to u square minus v square plus I times 2uv. So now, if this is entire, that means e to the power f square is also entire. It's a composition of functions is entire. Composition of two entire functions. That means e to the power u square minus v square plus 2iuv. This is entire. Okay, so now you call it G. So you look at mod G. Mod G is equal to e to the power u square minus v square modulus, because now times e to the power 2iuv, but uv are real functions, right? So this is 1, and this is constant, that means it's bounded. That means G is constant. So what is G? G of z equal to e to the power f of z whole square. So what does it mean by f square? F of z, this whole square, which is uz plus ibz whole square, which is u square minus v square plus 2iuv. So then what is g prime of z? This is e to the power f of z whole square plus times 2fz times f times z, and this is equal to 0. So you say that this is never 0. This is never equal to 0. So that means 2fz f prime z equal to 0 for all z inside C. Just wait a minute. Yeah. So that means f square z, this is constant, but it means that u square, it means that, see, f square, f times f is constant. That means, I mean, how do I put it? Right, yeah, but do you see that this means f is constant? So yeah, if f is non-constant, so yeah, f square is constant. That means at most f can take f of z. So f of z can take values in two different lines, right? So f of z equal to so f of z can be like minus plus, so it can be f square in the same line, so it is like this. Okay, so yeah, in these two lines it has to be, so that when you take the mod, it just goes here. Okay, square, it goes like here and here. Okay, so but again this open mapping theorem again contradicted, because this thing is not open set. So open set like would have been like this, but again this is not a. So yeah, you see that. So again I put in here, and f is inside these lines. F has to be on these lines. F has to be on these lines, and this is not open. So f of z in this lines, so not. Anyways, okay. So f cannot be non-constant function. So yeah, so f of z is constant. And now this question is it 4 or 5? It is 5. So let f is entire with image of f equal to b greater than or equal to 1. Then what can you say again? What can you say about f? Then again, here f is constant, but how do you put that? See, f is holomorphic. That means I times f is holomorphic. So I times f is holomorphic means what is f equal to, let's say, u plus ib. F equal to u plus ib. So I times f means minus b plus I times u. So f of f e to the power if, that is equal to e to the power minus b plus e to the power iu, and times. So if you take mod, this is mod, and this is 1. So, and now you see that v is less than equal to 1. That means e to the power v this, sorry, e to the power b greater than equal to 1 means e to the power b is greater than equal to e power 1. And that means e to the power minus b is less than equal to e to the power minus 1. So that is again, so it was entire, so it is if, this is I times f. Okay, this is entire. Entire means that is entire. So, but get e power if, this is bounded by E inverse. So that means e power if is bounded and entire. Use Liouville, that means e power if is constant. So then again g equal to e power if, then g times z g prime z equal to 0, which is I times z prime z into e power I of z. But you can check that this is not equal to 0. So that means I f prime z has to be 0 for all z inside C. So that means f prime z equal to 0 for all z. So that means f prime z, sorry, f is constant. Okay. So does anybody have some specific question in complex analysis would like to be solved here, or at least be tried, or any question so far, or any suggestion? Okay, question 6. So let f is entire and f satisfies the following: f of z mod of f of z less than equal to mod z cube by log mod z. This bound for sufficiently large, or let's say mod z greater than bigger, and this of course greater than 0. So what can you say? What can we say about f? Any suggestion? What can we say? Any suggestion from the audience? Hello. I mean, it is not visible. I'm just asking you. Okay, so let me tell. So then f is a polynomial of degree at most 2. So the proof is the following.
Sir, that you are writing on the whiteboard is not. We are not able to.
It is still not?
No.
It is not.
Yeah, it's not visible. Only up to the line f is constant. Only up to that. Okay, dear participants, let us wait for, yeah, Bappa Ghosh is joined back. Yeah, yes, your screen is now visible. Hello. Bappa Ghosh, I think you are muted now.
Yeah, hello.
Yes, Now it's fine.
Okay. So yeah, f f of z now on the ball b of 0 comma r1 is greater than r. We can define. We actually know that f of z is equal to summation of r n equal to 0 to infinity n z power n. Now why it is? This is because the function is entire, so it has this expression, the power series expansion. Okay. Okay, so now I have to show that this is a polynomial of degree at most 2. So that means that everything is 0 after 3. Wait a minute. Yeah. So and this is so I have to show that this is equal to 0. So that is, and this is, we know that 1 upon 2 pi I integration mod zeta equal to capital R1 and f of zeta by zeta to the power n plus 1 d zeta. So its mod is this. So that is less than equal to 2 pi integration mod zeta equal to R1 f of zeta's mod by zeta to the power by mod zeta whole to the power n plus 1 d zeta. So this is nothing but 1 upon 2 pi. This thing, you know that for all r less greater than, and I have written it this. So f of zeta, so this zeta is bigger than r, so it satisfies this thing, this property. So okay, so that is zeta to the power 3 by log mod zeta by zeta power n plus 1 mod zeta equal to r prime. So what do you get? This is equal to 2 pi and d zeta, of course, and this is 0 to 2 pi r prime. Here it was a mod, there was a mod r prime r1 to the power 3 by log mod r1 by r1 to the power n plus 1, and this is r dt. So what do you get? Here you get 1 r less, and you get 0 to 2 pi, 0 to 2 pi. So 2 pi by 2 pi into r1 to the power, this is r1 to the power, so okay, by 1 by, so log mod r1 times r1 to the power n minus 3. So for n minus 3, this is greater than or equal to 0. Do you agree? I assume that n is greater than or equal to 3. So this is greater than or equal to 3. So at least this is dominated by 1 by log r1, and this goes to 0 as I increase r1. So that means n is small as you wish, so n is 0. So, and of course n is greater than or equal to 3. So that means f is a polynomial of degree greater than or equal to 3. Okay. So yeah. One more question I want to do. Shall I, sir? Hello?
Yeah, yes, you can do one more. No problem.
Okay. Yeah, it's a bit. There's a little bit of computation in this question. Question number 7. Suppose f is a meromorphic function and e to the power f is a holomorphic function. Is also a meromorphic function. Then prove that f is holomorphic. Okay, holomorphic function on a domain D. Okay, meromorphic on D. So holomorphic on D. D is domain here, not the unit disk. Unit disk is this. Okay. So proof. So what does it say? So suppose you have a domain D, and it says that, so if f is holomorphic, then f is not if f is not holomorphic and f is meromorphic, that means f has some points where it is it has what is that called, a pole. It's a pole. Suppose it's a pole. Z0 is a pole. So that means that at the Z0 so there cannot be any pole like this. So what it happens? So what does f do? So diagrammatically I can prove it very easily. So what does f do? F sends this Z0 to infinity. We all know that if f has a pole at Z0, if has a pole at Z0, if and only if mod of f of Z0 this goes to infinity, Z goes to infinity as Z goes to Z0. So this neighborhood of Z0, the smaller neighborhood, that is, let's call it U. So that U is mapped to neighborhood around infinity. So this is this is my C hat and this is my infinity point. So it is mapped around the neighborhood in this neighborhood around infinity. And what does this e to the power z function does to this? Does anybody know that e to the power z has a that has an essential singularity at infinity. So singularity at infinity. So that will mean that it is going to, this neighborhood is going to be mapped on the whole of this C except 0. So if f is meromorphic, so if e to the power f is meromorphic, then it has to go to it cannot be some neighborhood here has to go to at the point, I mean in the neighborhood of infinity or to some neighborhood inside C, but it is dense in C, so it cannot be a, so e to the power f, this cannot be a meromorphic function because you see that this is dense. So our assumption was wrong, that f has a pole at some point. So every point where f is not holomorphic is actually f is not holomorphic is I mean there is no such point. Wherever all the points which were suspected to be not holomorphic, it's actually f is actually holomorphic there. So yeah. So is this diagram answer clear, or I can prove it algebraically? I can do the computations. Does anybody want me to do so?
Yes, sir. Please, if you can.
Yeah, thank you very much. So yeah, so let F has a pole. So basically whatever is done here, I will just explain. Okay, just this is the explanation. So F has a pole at Z0. So how does that? So what does that mean? So you know that pole at Z0 of order, let's say n or capital N. Then you can write f of z equal to z minus z0 whole to the power minus n times some g of z. So what I mean, g of z by z minus z0 whole to the power n in a neighborhood around z0. So and also you check that g of z0, this is not equal to 0, because what is its what do we mean by having a pole n minus 1 to infinity n z bar something plus or okay strictly greater than n z minus z whole to the power n. So and also you know that n is not equal to 0. This is what means f to have a pole at the point z0 of order n. So that and now when you take z minus z0 whole to the power n common, you get something like 1 by z minus z0 whole to the power n common here n plus n minus or n plus 1 z and so on. Okay, or minus n, it is actually minus. Okay, so this is what you get, and you can see that when you put here is z minus z0. When you put z0, these guys are 0. This part is 0, but this is not equal to 0. So you see that g of z0, this is not equal to 0, and that will be important here. Okay, so yeah, so now define. So you can so since g is continuous, you get we get another small neighborhood contained in the previous neighborhood, such that g of z is not equal to 0 for all z in that neighborhood. Let's say u prime contain in u, so and which is again contained in d. So you get for this. Okay, and then you can define this 1 upon f, which is z minus z0 whole to the power n, and of course minus z0 g of z0. And now this is extendable on, so for all z, this is z. So this is true for all z inside u prime. Okay, now you see that f of this is equal to f of z not equal to 0. So near so it is 0. That means f of z not, this is equal to infinity. So now So what does F do? So F maps a neighborhood of Z0 to a neighborhood of infinity. So what it does? It takes a neighborhood of Z0. This is my U prime to neighborhood of infinity. Since this is infinity, this is my infinity is neighborhood. This is map to here, and this point is goes to this, and then I have so e to the power f of z means this is f of z, e to the power f of z. So if f has a pole, so I'm saying that e to the power f is mirror. So I'm saying that e to the power f is meromorphic. So what is e to the power f? So it means e to the power f is g of z by z minus z naught whole to the power n. But you see that e to the power z, e to the power gz, this is holomorphic, and you have this z minus z naught to the power n here. But okay, so do you know that e to the power 1 upon z is it has it has an essential singularity at 0. So I'm just using this. So it means e to the power 1 upon z minus z power whole to the power n has an essential singularity at z naught. So which is what we have. So that means e to the power, and g of z naught, see, g of z naught is not equal to 0, or it's inside C, and e to the power g of z naught by z minus z naught, we get whole to the power n has an essential singularity at z naught. So this is more or less the calculation. So does anybody have any question? So I think, sir, let me. Oh, yeah, Dia, please ask. Dia and Ravina.
No, sir. Sir, please continue. I will ask later.
No, I thought nobody is going to ask, so I was going to say some general strategy. So you can just ask me some question if you want.
Actually, sir, I am pursuing MSc first year now, and this is complex analysis. Actually, a very new topic to me, and I am only just preparing. So I was asking for some books and so from where I can study this a bit.
Okay, so you can, to begin with, you can read ᴛᴇᴇᴛ, but that book assumes a lot of things, or it does, I mean, everything it does on a very suitable, I mean, very nice neighborhoods, or very nice open sets, which is not present in the book of Conway. I prefer Conway. I prefer reading Conway, but Conway is a bit, it's a step after ᴛᴇᴇᴛ. So what you do, you read ᴛᴇᴇᴛ a bit, and then you can switch to Conway.
Okay, sir.
Dia, in your graduate time, which book you have followed? Is it Churchill and Brown?
No, sir. Actually, I followed and from a Bengali writer, Joydeep Sengupta book. And
Okay. So for the undergraduate level, I think you can read Churchill and Brown as well.
Okay, sir.
I didn't know that. Okay,
Dia is
Bappa
Bappa Ghosh. Dia is now studying MSc in IIT Bhubaneswar.
Yes, sir.
Nice, very nice. Yeah, I think you are also from Bengal, right?
Yeah.
Yes, sir.
Yes.
I am from Kolkata.
Oh, okay. We'll meet probably after corona. Corona. Okay.
Yes, sir.
Yeah, Ravina, you had some question, I guess.
Yeah,
Yes,
Ravina.
sir. First of all, thank you very much for this very useful
Ravina,
session.
you can. Yeah.
And
Yes. Yes. Yes.
And
secondly, I
internet, I
just
think.
wanted to ask you the thing you defined initially about differentiability from some domain Rn to Rm, and you were talking about some metrics things. So can you suggest some material from which we can read this stuff? Because
Yeah,
in
yeah, it's
MSc
mathematical analysis, by Tom Apostol, or calculus 2 by Tom Apostol.
so can you write it in comment box, please?
Yeah, I'm writing it. So yeah, that's a very nice thing. Tom Apostol. It is mathematical analysis, and I mean, or another book. And the second book is also by Tom Apostol, and that is Calculus 2. Calculus 2. Okay.
Yeah, of course. I think in Rodin also there is a chapter on functions of several variables. In that differentiation and all that are
Yeah.
being
Also,
regarded as an operator in the matrix representation. All that I think it is there. Ravina is Bappa Ghosh. Ravina is from JNU, JNU Maths
oh,
Department.
hi. Yeah. So yeah, I mean, in which are you
Ravina?
a undergrad or postgraduate student, Ravina?
Sir, I'm doing MSc second year student.
Oh, I think this will be helpful for you in upcoming exams like NET, GATE, and NBHM as well. Yeah.
Yes.
Okay, sir. Thank you.
Yes, thank you. Thank you, Ravina. Others?
Hello, sir.
Yes.
Yes,
Am I
Sissy.
audible? Sir, today's session is very nice,
Yes, you are audible.
Yeah.
and actually, I'm doing my master's. And then actually, I am also from
Speak here.
Nadia
I
district.
cannot hear you. Oh, hi.
Yes, sir. And I done my graduation from Chakda College. Sir, which
Oh,
in which state you belongs to?
which?
You are from Nadia.
I'm from Krishnanagar. Yeah, I'm from Krishnanagar.
Okay, sir. Nice to see you. Sir, actually,
Yeah.
I want to ask you that in what is the right way to read any book or any theorem?
Okay, so the strategy I follow, or the strategy I have learned from my professors, also from MTTS, Kumar and all, that whenever you are reading some book, try to read in between the lines. So there are a lot of things those are said between two lines, a lot of steps not done in between two steps. Try to feel that on yourself, and do those calculation by hand, probably, and what else, and probably when you are reading a theorem, probably you just try to come up with your own proof. Most of the time that is not possible. We try to explain the proof that is written on the book, but the proof that is written on the book is actually the proof actually written backwards. So you have to go to the calculation first. So whenever, let me give you some example, quick example. We say that the sequence 1 upon n go to 0, right? The real sequence 1 upon n go to 0. And by that, what do we mean? We mean that for given any epsilon, there should be some stage n naught after which 1 upon n should be less than epsilon. Mod upon n should be less than epsilon. But we have to go from this thing that so what we want to find? We want to find 1 upon n should be less than epsilon. That means n should be greater than 1 upon epsilon. That is n epsilon greater than 1. And what is that? That is Archimedean property. So now in the book it is written in this way. So suppose epsilon is positive, and by Archimedean property you get n epsilon greater than 1. That is 1 upon n less than epsilon. So you take any n which is less than that, greater than that n. So you get 1 upon small n less than 1 upon capital N, which is less than epsilon. So it's not the way it is written in the book. It's the reverse way. In most of the time, the writer has thought out the solution or worked out the solution.
Yeah.
Okay, sir.
Bappa Ghosh, let me add one more point in that regard. Always, students are always advised to go through the standard textbooks, and also after reading one topic from one author, they can. It is better to go with another author also. So you may get some different views on the same topic, same concepts, different examples. So you will get more exposure.
Yes.
Okay, thank you, Tidhi. Tidhi is also from Kolkata, and she is now pursuing MSc at NIT Trichy, Tamil Nadu.
Wow, nice, Tithi. Congratulations. You took a giant jump from Chakda College to
yeah. From north to the extreme south.
Yeah. No, we are not at north, we are to the east of India.
Yeah. Yes. But usually we used to say that North Indians. That is right.
Yeah. So any other question?
Yes, others?
Hi, sir.
Yeah,
My name is Kavya. I'm a final year student of Marthoma College, and your class was really useful for us. Thank you for spending your valuable time with us. Thank you so much.
Thanks for attending the talk as well. Yeah.
Kavya is from Kerala. She is a final year BSc student. For BSc students, it may be a little bit difficult to follow all these things because all these are mainly the PG topics. But anyway, they are also studying something regarding Cauchy's integral theorem and all that in there, basically from the Churchill and Brown's book. In Kerala, we are following that book in the undergraduate level.
Okay.
Thank you, Kavya.
So, Kavya, I want to say you something. So, in the beginning, what I did, I actually, from sir, I actually came to know that there would be some undergrad students. So, I defined continuity first. So, you look at continuity, then to motivate the definition of differentiability, I bring the differentiability notation of one variable. So there, what do I mean by that derivative, except being just a real number, I can also look at that as a map from R to R. That was useful, and then I took it to Rn to Rm, and so you just try to follow this pattern. And if you see the book by Apostol or Apostol's any of the books, he has also he has also written that things exactly in the same order. So I think to make it accessible to you and the other undergrad student, I followed this path. I hope you can pick up from here.
Thank you,
there was a
Kavya.
question in the chat.
Yeah, in the chat box, it's actually, many students have this problem. During their MSc, they have very tight with their study schedules and all assignments and all that. Then how to manage to prepare for this competitive examination? I think you can have some tips for them.
Yeah, so at my time, what happened? It was actually a very until the examination, written exam of NBHM. It was a normal scenario. There was no COVID. There was no lockdown. There was no, online sessions and so on. And also my my NBHM exam, interview was also offline. The day I gave NBHM exam, it was I think Friday, and from Monday our institute declared holidays, and that was the end of every online offline classes. So so everything I gave was offline. So maybe now maybe you may get a bit of extra time or not, but let me say you. So what I used to do, there was some gap between two semesters, like 1 month gap. So in that gap, I revised everything that I studied in my MSc. In hindsight, it's a very rigorous course of MSc, and sometimes maybe I consider myself to be very lucky to be MSc student of hindsight. So, but anyway, so when you are doing MSc, you are also learning something, and also you have done some courses in undergraduate as well. So what I did, I revised linear algebra, real analysis, then complex analysis, functions of several variable, topology, a bit of algebraic topology, and then I looked at the question papers of various exams. The first to come was NBHM before the NBHM exam. So that's how I prepared for NBHM exam. NBHM exam was scheduled on January 2020. So we had a gap of around 20 days. Our class started in the first or second week of January, but we had a gap in the December, whole month of December, and 20 days in 10 to 20 days in January. That helped me to prepare for this NBHM exam. And for NET, I'm just talking about my NBHM and NET preparation so that you can get some view how I could prepare for it. Your preparation may be different, but yeah, if you can pick up from here something you see here, you can follow. So in NBA in June 2019, for preparing June 2019 NET, our exam was over by I think May 1st or 2nd week, and from that day only I prepared. I read everything those for me sequence and series of functions, and those things I reviewed, and then complex analysis, these things that I told today, and topology, linear algebra, and I tried only the pure mathematics questions. I recommend not to fancy that thing if you are not very much confident in pure mathematics only, and I had no other choice because I didn't know any differential equation, any partial differential equation, any probability, any statistics. So I had to stick to only the things which are typically called the pure mathematics portion. So, and I actually tried to keep myself calm inside the exam hall, and yeah, in the rush of adrenaline, we made some mistakes. Those are there, but I tried to keep myself calm. And in the exam, it happens that your adrenaline goes high. You can't see. Even if you read something that doesn't register in your mind, those things happen. That happened to me as well. That happened to others as well. Just try to keep your adrenaline as low as possible. It's up to you how you try. And moreover, in the phase of preparation, what I did, I took, I think 10 to 15 years question is available online of net. Okay, I downloaded all of them. I solved all the questions of at least from the pure part, which I could not do. I consulted some of my professors, and I had one or two of my friends with whom I prepared. I solved those questions. Like I gave myself 2 hours to solve the only pure part questions. So, towards the end of those exam sessions, my own exam sessions, it was taking roughly 1 hour, 30 minutes, 40 minutes, and not beyond 2 hours. In exam, you have 3 hours. So try to make that. Okay. So that is how I tried. I didn't get it. Was like
Yes, Bappa.
yeah.
Actually, the main problem with the students is that after their BS, at that time of BSc, they are not much in a serious mode as like B.Math students or integrated students in ICES or something like that. In a regular college, they have only very loose mode about the studies in undergraduate level, and while switching on to PG, everything will become highly rigorous and all that. At that time, they may have many adjustment problems and all that.
No, actually, I am also not a B.Math student. I did my M.Math, of course. I did my undergraduate from Presidency University, of course. It was also a very nice course, and also the syllabus was along the line of B.Math, not exactly copy paste of B.Math, but along the line of B.Math. We learned a lot of things in Presidency, of course. Thanks to that, I could cope up in the M.Math course, which is a really tough course. And sometimes you have to make the most of whatever you have. And also for the GATE preparation, I had nothing new. I just solved my, pure questions and pure mathematics questions, and somehow got the rank of 12. It was, I don't know how I got it in the GATE, but yeah, those were all based on the confidence of my net score and also how I performed in NBHM. So yeah, that's it.
Bappa, I
So
have
any other
seen
question?
name in many. Yeah. I have your name in the rank list of many interviews. Where your at different institutions.
Sir, you are not audible.
Really useful for
Sir, can you please
is it
say it
okay
again?
now? Is it okay now?
Yeah, it is. Yeah.
Is it okay?
Yes, it is okay. Yes.
I have seen name in many of the rank lists.
No, sir, it is not okay again. It is not okay again. Sir, you are not
audible.
Okay?
Yeah,
now
Bappa, I am asking you to share some interview experience because you have many experience at different institutes, interviews, attended many interviews, and in the rank list, in the front positions you are there. I have seen many times your name. So please share your interview experiences. That will be useful for them.
Yeah. So in the interview, before the interview, I got a lot of times. That's a positive thing happened to me. Probably it will not happen again because there was a 1 or 2 months gap because of COVID, or 2 or 3 months maybe probably. So I could, brush up everything. Not only brush up everything, I could read very seriously and rigorously. So in the interviews, the interviewers really were helpful in every institute, and they only ask you the questions what you are, in which portion of mathematics you are comfortable in. Like if you say I'm comfortable in analysis part of the subject, they will mainly ask you questions from analysis. They may ask you another preference either from topology or from algebra or from geometry. So you have to somehow prepare another portion of the subject. So for my preference were first analysis, then topology, then algebra, and most of the questions were asked from analysis and topology, and some few are from algebra. And professor used to really help. So suppose they ask a question and they don't really expect you can solve the question in the exam, in the interview itself, but they want to see how you approach the question. I mean, let's say suppose you are asked a question in major theory. Let's say in major theory there are 2 or 3 main theorems like MCT, DCT, BCT, and cathode extension theorem, and Fubini's theorem, and Fathou's lemma. These are the main theorems. So they will ask you one question which may be closely related to one of these theorems. In most of the interviews, it is the fact that a question is asked around some of the big theorems. Okay, so you will be asked a question around these things, and in real analysis, maybe you are asked some question around M test, Wester's M test, something like that. So you have to say that you are trying to use this thing, or even if you can say, I mean, what is the name of the theorem? You try to say this is the thing I am trying to do. This is the theorem I am trying to go into, or you draw diagrams and say that this is my domain and I am doing all these things. You won't believe in TIFR Bangalore, I was asked some questions in complex analysis. I just drew some picture and they were happy. I just drew some pictures and they were happy. So it is about, I mean, it is about your understanding, whether you have just understood. You may or may not remember all the theorems, all the definitions, everything, and speak in the interview. Even if you if you feel that you are not confident, try to speak. Sir, I am thinking this, and this is my whatever you are, the way you are answering, and yeah, and try to use these techniques. I just use these techniques.
Okay. Is there make some comments, please?
In chat there is something, I guess. Oh no. Thank you, Abhiya and Dia. And any other question from anyone?
Srilakshmi and
Thank you, Amit. Srilakshmi, Sari is asking if you have some question. I think she has some internet problem probably.
Yeah, sometimes. Lakshmi, are you there?
Yes, sir.
Yes.
So good afternoon, sir. Myself Lakshmi. I'm a third year BSc student from Kerala.
Yeah.
As Vinod sir said earlier, this topic was not much familiar for me because we are now going through the basics of complex analysis in our semester, sixth semester. So this session proved to be very useful because I got an idea, that brief idea about how the concepts coming in this complex analysis, and basically that topics like holomorphicity and all. So thank you so much for explaining such topics, and also thank you for sharing your experience regarding this interviews and all. Thank you so much, and thank you Vinod sir for arranging this class. Thank you.
Thank you.
Thank you, Lakshmi. Thank you.
Yeah, Lakshmi will probably try to see the you will try to see the difference between complex analysis and real analysis. It's the study of a differentiable function in 2 different categories. So you will see that somewhere it differs, and the place where it differs is the Cauchy-Riemann equation. That's the central idea. For that only everything is coming into the picture. Okay, you will see.
Okay, sir.
Okay. Yes.
Okay, any others? Otherwise, we may wind up here. Srilakshmi, are you there? Okay, any others? If you have anything to ask or comment, you can do it now. Feel free to ask.
Or you may send email to me. I'm just sharing my email address.
Okay. So thank you, Bappa Ghosh, for being with us on this day of
Sir,
and also your experiences in studying and in interviews. All that will be really inspiring for any student or any even aspiring. Happy to be as you are with us for such a session, and let us hope that in future also we may arrange some sessions for our students. Thank you very much, Bappa Ghosh.
yes, sir. Thank you very much for giving me this opportunity. Thanks for everyone for bearing with me in last almost 3 hours. Thanks everybody for attending the session. Also, you may ask question in the group. I'm also in the group. I'll try to
Yeah.
answer.
Yes. Bappa is in our Math Aspirants group. If you have anything questions, I will. Okay. Otherwise, you can directly send to me. I will forward to him, or you can send to his email. So nowadays, communication is not a big task, and also our groups have many members from various institutions. So it's actually it's a great community with lots of students from various institutes. So make use of all that opportunities that the technology provides us. Okay, thank you everyone, and wish you all success in your coming examinations. Thank you. Let us sign up here.
And also,
Bye.
Happy New Year.
Yeah, happy New Year.
And
Bye.
also, Happy New Year.
Thank you.
Bye.